Welcome. In this video we'll be looking at circuit analysis with a few examples of analyzing some electronic circuits. To analyze any electrical circuits, there's three components you need to master. First of all, you have to have a good understanding of the basics of series circuits. So first of all, let's consider 1 amp leaving the battery, 1 amp between the components, and 1 amp after the components. So in a series circuit, current is constant. Voltage of the supply, Vs, is 12 volts. Voltage across this first component is 8 volts. Can you predict the voltage across the second component? That's right, it's 4 volts. Because the voltage within a circuit splits up to equal that of the battery or the supply. So 12 volts leaving the battery can be found as 8 volts across the first component plus a further 4 volts across the second component. The voltage used up in the circuit once it leaves the terminal and charge returns back to the terminal, all that voltage has to equal the potential of the battery. We also have to have a good understanding of parallel circuits. So let's consider what happens to the current in a parallel circuit. In this example, we have a current of 1 amp leaving the positive terminal of our supply battery, travels down, and 0.4 of it goes through the first branch. We call this a branch because we have a node or a junction whereby some of the current will travel across this first branch and some of it will travel across the second branch. So if I started with 1 amp and 0.4 on the amp went through the first branch, can you predict what's left for the second branch? Of course, it's 0.6. And then when they combine back together again after the branches, we come back to 1 amp. So in simple logic, the current before the branch is 1 amp will be equal to the sum of the currents within the branches, and then when they combine will be equal to the current after the branch. Let's consider the voltage. We have here supply voltage of 12 volts, and in this circuit we find that 12 volts is across the first branch and 12 volts again across the second branch. So the takeaway point from this is the voltage within branches, within parallel branches, are exactly the same, and if there's no other resistors either before or after the branch, it will be equal to the supply voltage of the battery. And finally, to analyze circuits, you have to have a good understanding of Ohm's law. Ohm's law looks at three variables, where V is the voltage, and that's measured across a component. I is the current, and that's measured through a component. And R is resistance, which is measured in ohms. And here's our triangle that we use to make calculations using Ohm's law. First option is V equals IR. Second alternative, we want to make I the subject, I the current, is equal to the voltage over the resistance. And finally, we're after the resistance, it's equal to the voltage divided by the current. So let's look at one of two examples. So in this circuit, we're asked to find the value for I1 over here on the left, for I2 on this branch, and for R, the resistor in the branch. Let's go through this. Sometimes the challenges are where to start in this type of problems. It's like unraveling a ball of twine or string. You've got to start for the simplest part and work forward from there. So we have here in this branch both a current and a resistance. That enables us to use Ohm's law within this branch to work out the voltage drop across this branch. And we know that V equals IR. So we sub our values in, where I, the current, is 0.8 of an amp, and R, the resistance, is 10 ohms. So 0.8 times 10 gives me 8 volts. So I've got 8 volts across this branch. So 12 volts from the battery, the supply, is equal to, well, we know we've got 8 volts across this branch, and we learnt just a minute ago that any two parallel branches have the same potential difference or voltage across them. So there's 8 volts from this point to this point. We started with 12, we've used up 8 in this parallel component, and we have some left over for the voltage across the 2 ohm resistor. Well, quite logically, 12 is equal to 8 plus 4. Okay, so this 2 ohm resistor gets a 4 volts, and this is consistent with the rules we're looking at for series circuits. Whilst this is a parallel branch, the entire circuit operates in a series mode. So there's 8 volts across the parallel component of the 12, leaves us with 4 volts across the 2 ohm resistor. Now we can use Ohm's law here because we have the V for volts across this resistor, we have the R for resistance 2 ohms, and we can work out the current that flows through it, I1. Here's our equation, I equals V over R to find the unknown current. Voltage of 4 divided by resistance of 2 gives me a current of 2 amps So there's 2 amps flowing through to this point. So current leaves the positive terminal of the battery, 2 amps flows through and it hits this branch. So we've got 2 amps that flow through this point. In the bottom branch, we have 0.8 of an amp. 0.8 of those 2 amps travel down the bottom branch. What remains of the 2 amps for the top branch? So I2. So clearly I2 is the difference. It will be 2 minus the 0.8 on the bottom, leaves us 1.2 amps on the top. Okay, all we have left now to work out is the resistance R. Again, this whole parallel branch has got 8 volts from this point to this point in the circuit, which means the bottom branch has 8 volts across it, and the top branch also has 8 volts across it. So let's look at the top branch. We're asked to find the resistance R. We've got the voltage of 8 volts, and we know the current's 1.2 amps. We can use Ohm's law, R equals V over I, and sub in our values, a V of 8 and I of 1.2. This gives me a resistance of 6.6 recurring ohms, or we round it to 6.67 ohms. And that's the conclusion of this example. We've been able to find, using Ohm's law and knowledge of series and parallel circuits, I1, I2, and R. Using the PhET simulator to build and examine example 1, we have a battery, parallel resistors, hooking into a single resistor, and current flowing around. Okay, here's our circuit components, what it looks like. We can get rid of the current, so that's our circle with our symbols. Let's put the current back in. Okay, so first of all, we have here a 2 ohm resistor. This one was a 10 ohm resistor. We had a 12 volt battery. If I click on that, it comes up with 12 volts. I can also check that with my voltmeter on the positive terminal, the negative terminal. We've got 12 volts as we predicted. And we're talking about the voltage drop across this branch. There we go, it's 4 volts. Whereas the voltage drop across this branch we had was, it's 7.96 because we couldn't get exactly the resistance here we wanted with 6.67 recurring. So that means also current, it's slightly up, but we've got 0.8 of an amp in the bottom branch of our parallel. We've got 1.22. Now we predicted 1.2, but that's because we've got a resistance here of 6.5 rather than 6.66. Notice the current's the same before the resistor as it is after the resistor. We also found that there was 2 amps coming out. Once they'd combined, we had roughly 1.2 and 0.8. That should come together as 2 amps. It's 2.02 because of the additional current going through the top branch. Okay, so once again, our mathematical modeling with our equations and series and parallel circuits can be fully backed up by our PhET simulator. Our second example, a slightly different circuit. This time we're trying to work out what is the supply voltage or the battery voltage, what is the current at this point, top branch of our parallel, and what is the single resistor on the bottom branch. So let's have a look. I've got 6 amps coming along before it branches off or splits. From this, I see that there's 2 amps traveling along the base, the bottom branch. So I started with 6, 2 on the bottom, what's left for the top? So I will be the difference, it'll be the 4. 6, take away 2 on the bottom, leaves me with 4 amps on the top. We now know that at the top branch we've got a resistance of 3 and a current of 4. We can apply Ohm's law, V, the unknown, equals IR, to this information to work out with a current of 4 and a resistance of 3, we have a voltage of 12 volts. So I've got 12 volts in the top. We learnt just a minute ago that in a parallel circuit, each branch has the same amount of volts across them. So here, branch 2 will have the same voltage as branch 1, which we said was equal to 12. So branch 1 on the top has 12 volts, which means branch 2 on the bottom will have 12 volts, not across just this resistor or this resistor, but across the entire branch. There's 12 volts found across the entire branch. Not only is branch 1 equal to branch 2, but in this case, because there's no other resistors in the circuit, that will be equal to the supply voltage or the voltage of the battery. So we had 12 volts in the bottom branch, 12 volts in the top branch, without any other resistors in the circuit. That means our battery must have been delivering 12 volts as well. Finally, we want to try and work out this R value. Let's look at the steps involved. We have a calculation here. For this single resistor, we know that 2 amps flows through both R and the 3 ohm. So on this 3 ohm resistor, we have a current of 2 amps, we have a resistance of 3 ohms, and we can calculate the voltage across this single resistor. So this is not the entire branch, just this single 3 ohm resistor. Using Ohm's law, the V equals IR, we find with a current of 2 and a resistance of 3, that the voltage drop across this single resistor is 6 volts. Now, not long ago, we discussed the fact that the bottom branch, the top branch, and the battery all have the same voltage in this case. So there's 12 volts at the battery. That will be equal to 6 volts across the 3 ohm, plus whatever voltage we have across this other resistor, our unknown resistor. 12 volts across this branch and this branch, 6 across the first resistor, which means we have 6 remaining for the second resistor. And finally, we can use this information across the second resistor. We know the voltage is 6 volts across this single resistor, and the current traveling through it, much like the 3 ohms, 2 amps across both of these resistors in the bottom branch. So V equals 6 and I2 equals 2 amps. Using Ohm's law rearranged, R the unknown equals V over I. So in this case, the voltage was 6, the current was 2. That gives us a final resistance of 3 ohms. Looking at our second example through a FET simulator, you can see we've got the circuit with the battery, 1 resistor, 2 resistor, 3 resistor, the same construction. Let's look at the variables we were given. We were told that we had up on top 6 amps, so we can read here that we have 6 amps. We were told in the bottom branch that we had 2 amps, which is correct. We're also told that our resistor, if I do these a quick flick, our resistor here was 3 ohms. Our resistor here has been set to 3 ohms, and we don't know this resistance, and we don't know this voltage, we don't know the current. So if we want to let that run and show the fact that the circuit does run with current flowing through, we can check again the current that we calculated going here was 4 amps, and it's verified with 4 amps. And the resistance that we had over here that we weren't sure of, it is 3 ohms, as we were proving earlier in our calculations. And finally, the voltage, to make this all work, the voltage across this battery, I think we calculated to be 12 volts, and it is in fact 12 volts. So everything that we did mathematically, we can prove using the FET simulator as well. Thank you for watching this video. I hope these examples and explanations of parallel series and Ohm's law made sense to you and help you to analyze circuits better in the future. Could you please like, share, comment, and subscribe? And as always, thanks for watching.